So let's get started. So welcome to my talk on a pattern language for microservices. It's really two aims of this talk. One is just to describe how patterns and pattern languages are in general a good way to talk about, describe, think about technology, applicable to a whole wide range of areas. But then in particular, why a pattern language for microservices is a good thing. So actually, in the little bit of time I have, I'm going to explain the pattern language and describe in detail some of the patterns. So, for those of you who don't know me, I'm Chris Richardson. I actually was born in England, but I've lived in the San Francisco Bay Area for the past 25 and a bit years. I actually got my start in programming back in the mid to late 80s, building Lisp systems, runtimes, compilers, garbage collectors, all the way up to GUI IDEs and the like, back when machines only had 8 megabytes of memory. That was actually a useful amount of memory. And then, of course, eventually I ended up programming in Java. And then back in 2006, my book, Pojos in Action, came out, and that was all about how to build applications with Spring and Hibernate, which back then were revolutionizing how we built enterprise Java applications. And then back in 2007, I started tinkering around with what was then a rather obscure service, Amazon EC2, which I think everyone has heard of today. And that sort of got me super excited. I created an open source project which evolved into my startup Cloud Foundry that was a Java platform as a service for deploying Java applications on Amazon EC2. Of course, today the name lives on in a totally different technology stack and so on. And Cloud Foundry was acquired by SpringSource shortly before SpringSource was acquired by VMware. So that was back in 2009. And I like to joke that the fish are not drawn sort of in scale in terms of market capitalization. Otherwise, I would be fabulously rich. My own jet, island, etc. Cloud Foundry was much more of a plankton than a sort of than a fish. So I was there for a number of years. Left actually 2.5 years ago. And pretty much today I do sort of all things microservices. So I do a lot of consulting and training around microservices and sort of modern ways of building software, which of course includes the microservice architecture. And I'm also the founder of a startup that's building a platform that makes it easier for application developers to write microservices. And it's all about event sourcing and CQRS and DDD and that and so on. So please go check it out, looking for feedback to shape the direction of the platform. A few other links in my GitHub repo. There's various examples of microservices. I also have the website microservices.io, which is all about this pattern language, so you can read up in full details of what I'm talking about today, my blog, Twitter, my startup, and so on. So here's the agenda. It's kind of like, why a pattern language for microservices? Why should we care? And then after that, I'm going to talk about various different aspects of the pattern language. So the core patterns, monolithic architecture versus microservice architecture. I'm going to dive into detail deployment patterns, the different ways that you can deploy microservices. And then at the end, I'm going to just briefly survey a few of the other patterns in the pattern language. There's quite a lot, and it takes hours and hours to go through them all. Right, so why a pattern language for microservices? So back in 1986, Fred Brooks, mythical man month and all of that, said that in software engineering, there are no silver bullets. In other words, there are no techniques, technologies, etc., that you could adopt that would give you a 10x boost in productivity. Interestingly, there are a lot of techniques that if you adopt will give you a 10x reduction in productivity. But really, there were no silver bullets. But that was a long time ago, right? And yet 30 years later, developers are still arguing passionately about their favorite silver bullets, absolutely convinced that if you adopt such and such a technology, it will give you a massive boost in productivity, right? You know, today, popular silver bullets include the Go language, functional programming, Node, Docker even, and of course, sort of JavaScript in general. Pains me, by the way, to think that, you know, I've been building software for 30 years, and really, Go and JavaScript are the best we can do, really? Anyway, slight dig. Kind of like describing myself here. You know, a lot of arguments sort of follow this suck-rock dichotomy, term characterized by or coined by Neil Ford, which is where your technology sucks, my technology rocks, and you sort of see these pairwise arguments: JavaScript versus Java, right? Spring versus Java EE, functional programming versus object-oriented programming, containers versus virtual machines. So you see these very polarized debates where my technology is incredibly good and I can't see anything wrong with it, whereas I can see all of the flaws in your technology and none of the good, right? Very polarized debates. So, you know, there's a lot of passion. Not only that, if you look at how technology gets adopted, it all tends to follow this kind of hype cycle, right? Whereas, you know, new technology comes out, there's just increasing hype around it, right? You know, people just believe that it's incredibly awesome technology that's going to solve all known problems, world hunger, and so on. And so it all kind of rapidly races up towards this peak of inflated expectations. And you think about where, you know, we look at this conference is about microservices, and you can actually see that rapidly rushing up towards the peak of inflated expectations. Docker's heading up there. And lots of, you know, exciting new technologies are up there. But of course, all technologies actually have drawbacks, right? And it's at some point, these drawbacks become recognized and projects start having issues and there are failures and so on. And then suddenly the whole kind of hype switches to, well, this technology is not any good, right? And sort of hype and level of interest plummets down into what's known as the trough of disillusionment. But then, of course, people start to realize that, well, every technology has both good and bad, and it's really how you use it that kind of defines success. And then it starts heading up, and the trade-offs are well understood, and you start heading up towards this, well, the slope of enlightenment, towards the plateau of productivity, where people have finally accepted there are right ways to apply a particular technology and wrong ways, and so on. And pretty much everything kind of follows this cycle. And it's kind of like, why is this? Well, if you look at look at a metaphor that cognitive psychologists use to explain how the brain works, they actually use the metaphor of an elephant and a rider. And the elephant represents the emotional part of our brain. You know, it turns out we are actually emotional beings, right? And that's actually how we make decisions emotionally. And then the rational part of our brain is like the rider. You know, it tries to point the elephant in the right direction and sometimes succeeds, but, you know, the elephant can go wherever it wants, right? And in fact, the rational part of our brain is often used to come up with justifications for decisions that the emotional part of our brain has already made. And if you just accept that, it actually explains an awful lot about the world, right? Donald Trump, for example. Though actually, given that he lost the other day, that joke's not quite as funny as it was last week. But you know, you just think, we are emotional beings. That explains pretty much everything strange and peculiar that goes on in the world. But despite this sort of fundamental limitation of our sort of infrastructure in our heads, we as engineers actually do need a better way to discuss and think about technology, right? We need a framework that can enable us to make rational choices and a framework that will enable us to deploy technology appropriately. And one approach that I find fascinating is the notion of a pattern. So the idea of a pattern is nothing new. The book, the Gang of Four book, I think came out in 1994, so 20-odd years ago. And it was a collection of design patterns, and of course they went through their own hype cycle, where for a while there was an expectation that you should design everything using design patterns, right? That was popular probably 15-odd years ago. But just ignoring that and just taking a step back and thinking about, well, what is a pattern? So a good definition of a pattern is that it's a reusable solution to a problem that occurs in a particular context. And the notion of a problem occurring in a context is actually incredibly valuable, right? Because where and when you apply a technology really is, and whether you're going to be successful really does depend on the context. So just at a high level, this pattern stuff seems to have something interesting to it, right? Because in one context, you might use one approach to solve a problem, whereas in a different context, you could use a different approach to solve the same problem. It really is context that absolutely matters. Moreover than that, the structure of a pattern tends to provide a great framework for discussing and thinking about technology. Patterns actually have a bunch of different structures, but here's one that I like, right? So every pattern has a name, so that sort of describes the pattern, describes the solution. It actually has a context, so that's the situation in which you're trying to solve a given problem. Obviously, there's the problem that you're trying to solve. Then there's this concept of forces. So these are the issues that you're trying to address within a given to solve a problem inside a given context. And interestingly, these issues can actually conflict. So there might not be an optimal solution to a given problem. You just kind of have to make various trade-offs. There's also the solution, right? The actual approach, the technology that you're applying to solve the problem in that given context. And then it gets really interesting. There's this notion of a resulting context. What are the consequences of applying this pattern? And which actually includes both some benefits and some drawbacks. I'm going to talk about that quite a bit on the next slide. And then there's also related patterns. So what are patterns that are somehow connected to this particular pattern? And as you're going to see, they could be patterns that solve the same problem in a different way, or patterns that solve problems that are introduced by applying this particular pattern. So there's a lot of structure and rich kind of ways of thinking kind of built into this pattern structure. So you look at resulting context, right? Applying a pattern has benefits. So, good things happen when you apply this pattern. It also has drawbacks. Bad things can happen, or there can also be just issues to resolve. So you think about microservice architecture, right? That enables you to go faster. Drawbacks, well, it adds a bunch of complexity. And then there's actually a whole host of issues that you have to resolve. So for instance, you're building a distributed system. So we need an RPC mechanism. Distributed systems can suffer from partial failure. So we might need a circuit breaker mechanism. We need service discovery and so on. So it's like, yeah, we're going to apply the microservice architecture, but there are these significant drawbacks to it, plus a whole bunch of issues that we have to resolve. And all of that is captured quite nicely within the pattern format. And then on top of that, there are related patterns. And there's sort of two main types of relationship. So there are patterns that provide alternative solutions. So you could think of the monolithic architecture and the microservice architecture as being alternative ways of deploying your system, right? You pick one or the other. Then there are also patterns that solve problems introduced by applying this pattern. So you could think of circuit breaker as a pattern that you then have to apply if you pick the microservice architecture. Likewise with service discovery and API gateway and so on. So what's nice is you can think of these patterns as forming this web of interconnected patterns. And this is particularly valuable because patterns now point to one another, and so they actually provide guidance on how to solve a particular problem, right? Where if you're looking at one pattern, it actually says, well, you should go think about these other patterns because they solve the problem in a different way, or you should go look at these other patterns because they solve the problems that I introduce. So it sort of just gives you guidance on if and when to apply a particular pattern, or more generally, a particular technology. And the whole concept of pattern language actually came about because of a real-world architect, Christopher Alexander. He wrote this fantastic book, A Pattern Language, and that actually describes patterns for, well, basically designing everything all the way from where should you position a city, which turns out to be next to water, right? Because water, trade, and all of that is important, all the way down to how do you design a room. And it's like, well, you want to have light on two sides and everything in between. Absolutely fascinating book. And he was kind of surprised in the mid-90s when he got invited to keynote at software conferences because he developed quite a following, because that inspired the Gang of Four book and so on. Okay, so that's the pattern language. And I guess you can, it's kind of worthwhile to be meta in the sense that, so you think about, well, I'm proposing that the way we should talk about and reason about a technology is to apply the concept of patterns or to write things up in the pattern format, right? And the benefit of doing that is that it's more objective. It's much more balanced. You get to see what the trade-offs really are. The downside is that it's less exciting, right? There's not quite as much hype. Unlike the sort of related pattern, which is everything is awesome pattern, right? Everything's wonderful, everything is great, which is sort of the prevalent pattern within the software community today. So, it gives you a bit of objectivity. So anyway, that's sort of my philosophical part of the talk. I want to talk, get into the actual microservice pattern language. So this is basically, the pattern language. It's a collection of patterns. It's actually still very much work in progress, and every so often I add a few more patterns. There's actually another one I've almost published, Microservice chassis, that covers things like Spring Boot, Spring Cloud, GoKit, and so on. So you can see there's a variety of the patterns are kind of grouped together. So there are the core patterns. There's monolithic architecture and microservice architecture. So those are sort of the top-level decisions that you kind of get to make, right? And you can see that they're connected by a dashed double-headed line, which says these are alternative solutions to the same problem. Then there's deployment patterns. There's various different ways you can deploy microservices. You could deploy them in containers. You could deploy them in virtual machines. Or you can just run multiple services on some box that you've given a cute name to, right? And you can see that those are pointed to by a single arrow solid line, which says these patterns solve problems that are introduced by the microservice architecture. There's also this hollow arrowhead that says these patterns are specializations of this pattern. So there's sort of this general pattern, single service per host, and a host could be a virtual machine or it could be a container. So there's sort of, little kind of schematic up there. And you can find this on microservices.io. You don't need to take a photo of it. Now, because it's a distributed system, right, microservice architecture is basically a distributed system, there's a whole bunch of patterns to do with inter-process communication. right? So there's the API gateway, which I'll talk about in a little bit. There's patterns around style of communication. Do you use asynchronous messaging, like Fred George is a fervent believer in? Or do you use sort of REST, right? Say the Netflix approach, or do you use both, right? Depends. So obviously trade-offs. Then there's a whole bunch of patterns around service discovery. So if you want to, service A wants to make a request to service B, it actually has to know the network location, the IP address, and the port of a service instance to talk to. In a modern architecture, that's a non-trivial problem. You can't just use a configuration file with a hardwired set of IP and ports, right? You need a much more dynamic mechanism. So there's a whole bunch of patterns around that. And then most of these patterns are really at the sort of the deployment level, sort of infrastructure level. And they don't really impact the application developer quite that much. But then there are I'm starting to work on sort of application level patterns. So, one of which is, database per service, right? So there the notion is every service has its own data store, database, private set of data that no other service can access. And then that gets you into the issue of how do you maintain data consistency across all of these, across multiple microservices, which pushes you in the direction of an event-driven architecture, which can lead you to event sourcing as sort of the way of constructing your business logic. And so it goes on. So that's sort of the big picture notion of the pattern language. I now want to spend some time talking about the core patterns, namely monolithic architecture versus microservice architecture. In other words, why are we here today, right? Standard example, right? So imagine you're building an online store, sort of Amazon-type approach, right? Type site. So you're going to have a presentation layer. You're going to have various sort of chunks of business logic, catalog service that's got all the product information, recommendation service, review service, order service. So just kind of modules, probably serving up HTML to a browser or exposing a REST API to some kind of mobile client, relational database in the back end. So you've got this nice layered, logically modular architecture, but then it's like, well, how are we going to sort of package all of this up and deploy it, right? So what are the forces? Well, I think by far an overriding force today is businesses need to innovate faster and faster, right? And since we as software developers are writing the software that's automating the business processes, that actually means that we have to develop more complex, higher quality software faster and faster, right? So that's a major force that's affecting software development today. So we need to be productive. We need to write code that's easy to understand and modify. We need to do things like continuous deployment. We really need to leverage new technologies as they sort of prove themselves, right? Because technology tends to get better. We want to take advantage of it. And then there's sort of a mundane thing. We need to run multiple copies of applications in order to sort of deal with availability and scalability requirements, right? So one option, of course, is to use the monolithic architecture. So take all of our code, package it up as one thing, one ginormous application. So in Java world, that would be a WAR file. In Node, it would just be an application in the directory, and likewise with Ruby and so on. So we just build one thing, the application. Pretty standard architecture, right? Examples are just everywhere. Anyone know where this is, by the way? Yeah? Exactly. It's Ayers Rock in Australia. It's like thousands of miles in the middle of the Australian outback, like 1,000 miles from anywhere. Beautiful place. Shame to use it as an example of something that's got negative connotations here. But I was just looking for a monolithic rock formation. So, monoliths are everywhere. I mean, I have a theory that inside every enterprise, their core businesses are basically unmaintainable monolithic applications, right? But the reasons for adopting this architecture, it's simple to develop and test and deploy. All of our tooling is sort of oriented around building the application, right? Deployment is a matter of copying the application onto a server that's got Tomcat on it and restarting Tomcat. Scaling's easy because you can just run multiple copies behind a load balancer and you're good to go. Problem you have, right, is that applications have a habit of growing, right? You don't just build an application and stop development. The team just keeps adding functionality day after day, week after week, year after year. And if you keep that up, you're likely to end up with a humongous application, right? 100,000 lines of code, 500,000, million, or 5 million lines of code. And the trouble you have with applications that are getting that big, it's not quite sure where it starts to go bad. I also, at one point I thought it was, a million lines of code, but then I've talked with people who have had issues with 50,000 lines of code, right? Is that basically you end up in a situation where everything is slow and painful. Agile development and deployment basically becomes impossible, right? The code base tends to just intimidate developers. So this is the pyramid at Giza. I hate to use that as a negative example as well. But there's just too much code, too much complexity for any developer to fit in their head, which means that when it's time to make changes, you don't really know how to make a change correctly. And that tends to sort of be a downward spiral, and you just end up with an unmaintainable big ball of mud. It's an obstacle to continuous deployment. You're likely to have an extensive manual testing phase, and you end up having very infrequent releases, which actually increases the risk of failure and so on. Scaling can be a problem because inside that one monolith, you could have a bunch of modules with very different scaling needs. Some of them could need a lot of memory, others could need a lot of CPU, others could need a lot of I/O, but you've packed them together, and so you can't sort of deploy each one separately on the hardware that's sort of optimal for it. Think about picking an EC2 instance type, right? They've all got different characteristics. Large applications tend to overload your IDE. Weirdly, the horse is in front, doesn't seem to be overloaded. But in the real world, the larger your code base, the slower the IDE is going to get. Likewise, the application server will take a long time to start up as well. And if that's all part of, if having to restart an application server is part of what you have to do many times a day as a developer, it's, if your application is going to take 5, 10, 15, 20, or in some cases 40 minutes to start up, you're not going to be very productive, right? Also, even though you've got a logically modular architecture, if everything has to end up in the same, say, WAR file, the same application, that means getting changes into production can take a lot of communication and coordination between all the various teams that are working on the application, right? You can imagine the UI team wanting to push updates to the UI, but then they can't because the back-end team went and checked in a bug, and so the application's not in a releasable state. And so it's kind of painful. And then also, a large monolithic application tends to couple you to the technology choices that you made at the start of the project, right? I think I heard that earlier today in one of the talks. you can't necessarily easily adopt some brand new framework, right? Because that would actually require rewrite of everything, which if that's 100,000 lines of code, that's time consuming, risky, and so on. So you tend to be stuck with whatever technology you picked at the start of the project. So in summary, right, you've got this unmaintainable ball of mud that's getting in the way of the business innovating as fast as they want to, plus it's written in a technology that no one wants to use. And so you're often in a world of pain. Anyone here like that, or are we all like in the microservices? All right. Okay, so the solution, of course, to those problems is to use the microservice architecture. And good question to ask is, what's the definition of microservices? Well, a few years ago, I read this book, The Art of Scalability, which was written by some people who were at eBay and PayPal. And in the book, they described the scale cube that's a three-dimensional model of scalability. So there's three different ways you can scale your application. So along the x-axis, they've got horizontal duplication, which just means running multiple copies of your application behind a load balancer. So that's our typical kind of scaling. We do that every day. Along the z-axis, they have data partitioning, which is where you still run multiple identical copies of your application, but instead of using a regular load balancer, you're using some kind of routing component that looks at some attribute of the request and decides which server to route that request to. So in the database world, that would be sharding, right? Where you use the primary key of a row to determine which server that row should reside on. And you can do something similar at the application level as well. But X and Z axis scaling are all about basically running monoliths, running identical copies behind some kind of load balancer, some kind of router. So where it gets interesting is y-axis scaling or functional decomposition. And the idea here is that you break up your system by function, right? So you're functionally decomposing it into a set of microservices. And that, for me, is that's my definition of what microservices is about, is y-axis scaling or functional decomposition. So if we apply that idea to the online store, we end up with an architecture that looks like this. So what were otherwise logically sort of modules now become standalone services. We can also functionally decompose the UI because sort of the web app part of your application can itself be quite complicated. And there can be value in having mini web applications for each part of the UI. So checkout, for instance, is handled by the checkout UI web application. Once we've done that, we can develop and deploy and scale each of these applications independently, so we can apply X and Z axis scaling to them. So one thing to bear in mind is that the goal of partitioning is to sort of break things up so that most changes only impact a single service, right? And that's going to enable us to sort of parallelize development, so we can work on all of these services independently without a whole lot of coordination between the developers who are working on each service. And also, the sort of a secondary goal of partitioning is also to allow proper scaling. So we separate components that have conflicting resource requirements. So we can put CPU-intensive components on machines that have a lot of CPU, memory-intensive components on machines that have lots of memory, and so on. So each one can scale more optimally. So lots of examples of microservices. Anyone know where this is? Yeah, it's a little closer than there as well. So this is actually Cappadocia in like, I suppose, eastern Turkey. these sort of fascinating rock formations. It's about the only thing I could find that was sort of, I don't know, the opposite of a monolith, basically. Classic example, of course, is Netflix, right? Probably don't need to say anything about that. Amazon, they migrated to a microservice architecture many, many years ago. They talk about how to render a page requires invoking hundreds of services. eBay, the auction e-commerce site, interestingly, Amazon and eBay both had monolithic architectures, and then they evolved into what you would now call a microservice architecture. So those are the classics. I think I've had this slide for like almost 4 years now. Obviously more modern examples, right? Like SoundCloud, Yelp, actually I use Yelp for restaurants, but they review other kinds of businesses. And then, of course, Uber, probably not a good example to use here. It's sort of increasingly popular architecture, right? Bunch of benefits, obviously, right? Simpler, smaller applications that are individually a lot easier to understand. We avoid problems with complex class paths. They're faster to develop and deploy. You can scale development a lot easier. They can be developed concurrently. It improves fault isolation, so a memory leak in one of them will not impact, in one service is not necessarily going to impact the rest of those services. Unlike, with a monolith, it will just bring down the entire thing. Scaling is easier. Then it also eliminates any long-term commitment to a single technology stack, right? So whenever you start developing a new service, you're free to pick whatever technology seems the best fit for that particular service, right? Or if you're making changes to an existing service, you could throw it away and rewrite it from scratch using the latest new shiny technology. So, so maybe one day it's Java, and maybe for some reason you'll want to rewrite it in Rust, for instance, or Haskell. I like Haskell, but so it also provides this, gives you the opportunity to sort of safely experiment with new technologies, because you're never making a massive commitment to a given technology, which is good. Bunch of drawbacks, right? Obviously, by far, the biggest drawback is complexity, right? Microservice architectures just have all this complexity associated with them, right? You're now developing a distributed system, so you have to deal with things like RPC and partial failure, right? You never had to worry about that in a monolithic architecture. You've split up services, which means you've split up databases, which then means that you have a challenge implementing business transactions that span multiple databases, right? So that pushes you back. Instead of having an ACID model, you're now using a base model, so that basically available, soft state, eventually consistent. So you typically have an event-driven, eventually consistent model, which takes a little while to wrap your head around and is not quite as simple as the ACID transaction model. You have all of the complexity of testing a distributed system. Like say if you've got a monolith written using Spring Boot with a few annotations on a test class, you can launch that application and then just start hitting either the UI using Selenium or the REST API. Whereas you want to test a service, well, there's a whole tree of dependent services. Do you spin them up as well? And it's just a bunch of issues around that. And plus all the operational complexity of instead of having a few instances of a large monolith, now you've got maybe tens or hundreds of different services that each have to be sort of deployed independently of one another. Then if you have features that span multiple microservices, then a whole bunch of coordination is required to roll those out. But so there's a lot of complexity here, but what I like to think is that this kind of complexity is manageable, right? In the sense that there are sort of solutions that exist, like automation. There are microservice testing strategies, as described by Martin Fowler. There's deployment technologies like Kubernetes, Docker or Kubernetes, or even a PaaS like Cloud Foundry that can automate the deployment of all of these moving parts. There's libraries for doing inter-process communication and Hystrix for handling partial failure and so on. So there's sort of technologies that deal with each one of these problems, whereas if you have a large, complex system that's sort of an unmaintainable big ball of mud, there's nothing you can do about that. It's just going to suck, and it's just going to get worse over time. So this can have pain, but it's sort of far less pain. So I'd like to think that the benefits of microservices sort of outweigh the drawbacks for large, complex applications. So you don't need to go home right now. Having said that, there's a whole bunch of issues that you have to deal with. How do you deal with deployment? How do you deal with communication? And sort of how do you partition it up? How do you deal with distributed data management problems and so on? So I want to talk really briefly about different deployment patterns. So the issue is, well, we've got a bunch of microservices. How do we deploy them, right? Bunch of forces, issues that you have to deal with. So the services are written using a variety of different languages and frameworks, or even versions of languages or frameworks, right? Each service is going to want to consist of multiple instances at runtime, both for throughput and availability. You want the act of building a service and deploying it to be fast. You want to be able to deploy and scale each one of these services independently of one another. You want to isolate services from one another so that a malfunctioning service isn't going to impact some other service. You really want to be able to constrain the resources that a given service instance uses, and deployment should just be fast, or it should be reliable. It shouldn't be an error-prone process that causes stress and keeps people awake all night, right? It should just be a smooth, easy process, and it also should be cost-effective. Because most companies outside Silicon Valley actually need to be profitable. So we have to watch budget and cost of hardware and the like. So there's a bunch of patterns that you can use, right? So there's sort of two main options: the more traditional multiple service instances per host, or a single service instance per host, which translates into either a service instance per VM or a service instance per container. So if we look at multiple service instances per host, that's the whole kind of traditional model where you get a machine and you run a bunch of service instances on it. The services themselves each one could be an individual Tomcat, if you're in the Java world, or it could be an individual node process. Or you could even run multiple services within the same process, right? You could actually have multiple WAR files deployed on the same Tomcat, or multiple OSGI bundles deployed inside the same OSGI container. There's a lot of variety here. So there are some benefits to doing things this way. One is you get very, very good resource utilization, right? Multiple services on the same machine means that they're sharing that one machine and its operating system. If they're within the same process, then they're sharing the same runtime. And deployment tends to be fast. You just copy the application to the machine and start it, and you're good to go. Downsides, of course, is that you get very bad isolation, right? if they're separate processes, there's a certain amount of isolation, but if they're, within the same process, there's next to no isolation. And even then, you can't, they can interfere with one another. A process could consume all of the memory or all of the CPU on a particular machine. Also, whoever's deploying it has to know this is a node. This service is written in node 0.10 versus 0.12 versus, what's it now, 4.x, right? And you have to, there's sort of a lot of detailed knowledge that has to be communicated from development to the operations people in how to deploy a particular service. So it's so there's some challenges that make it sort of somewhat unreliable. So the other option, of course, is to have one service instance per host. So you could do what Netflix do, take a service, package it up as a VM image, or an AMI to use EC2 terminology, and then at runtime, each service is a EC2 instance or a virtual machine or an EC2 instance that's sort of forked from that virtual machine image. Examples of that, of course, Netflix, it's a great example. They have an open source tool, Animator, which may or may not be sort of deprecated. Packer.io is a popular way of automatically building virtual machine images. There's also a company, BoxFuse, that builds super lightweight virtual machine images that are like fast to build and have fast to boot as well. So a bunch of benefits to this is, so if you package each service up as a VM, you get excellent isolation, right? Because that's what VMs are about. You get great manageability because each service instance is a VM. The virtual machine technology encapsulates whatever underlying frameworks and languages you're using. Once you've packaged it up as an AMI, you just create VMs from it, regardless of whether you're using Node or Java, etc. And you've got mature infrastructure like AWS for auto-scaling and load balancing and so on. The downside is you've got less efficient resource utilization, right? You've got a whole overhead of a virtual machine to run your tiny little 128 megabyte node process, for example. Also, the process of building a virtual machine image and booting a VM tends to be relatively slow. Minutes, which today is like a lifetime. So the other option is to use containers. So you take a service, package it up as a container image, and then each service becomes a container that, along with multiple other containers, is running inside, typically, a VM on top of a hypervisor. This, by the way, was the 400-meter-long container ship that was in the port of Oakland at the end of last year. I think it has like 18,000 containers on it, right? It's a whole lot of containers there. And of course, today it's all about Docker, but Solaris Zones is another containerization technology. You probably want to use some clustering technology on top of just raw Docker. So there's like Kubernetes, Mesos Marathon. DCHQ is a startup that has a GUI for those who don't want to deal with setting up Kubernetes. There's a bunch of benefits to using containers, right? So like virtual machines, they have good isolation and manageability. The container API becomes the API for managing the service. So once you've packaged your service up as a container image, it's a black box at that point. You do not know what's in it, which simplifies the information flow from development to operations. Unlike VMs, you get very efficient resource utilization because the virtualization is happening at the OS level, so all of the containers on a machine are sharing the OS. Deployment is very fast. Container images are typically very fast to build. So on my laptop, I can build one within 5 seconds. And then actually moving it into production probably just takes about another 50 seconds. So that's quite speedy. Downside is the actual container technology is not quite as mature as virtual machine technology, but though it's sort of maturing fairly rapidly. But something to watch out for. Now, in the remaining 30 seconds, I quickly want to survey some of the other patterns. So as I mentioned, this is a distributed system, so there's a whole host of issues, right? Like, how does a client outside the system interact with what are now tens or hundreds of services? Who does it talk to? And then also, how do the services within the system interact with one another? So as I mentioned at the beginning, there's a whole bunch of patterns to deal with this, right? So to handle the interaction from the outside world in, you typically want to use an API gateway. In terms of communication styles, you should use either messaging or remote procedure invocation, or maybe a combination of both. In order to solve the problem of how does a client of a service figure out the network location of a service instance to talk to, you have to use a whole set of discovery patterns where you have a service registry that's a database of service instance network locations. So there's patterns around how do you look things up and how do services get registered. And then at the application level, there are issues like what's the database architecture? And in order to promote loose coupling, you want to have a database per service. You might also want to use a mixture of database types, right? So that's the pattern there. But the interesting thing there is that introduces distributed data management challenges. And so that pushes you in the direction of an event-driven architecture, which possibly uses event sourcing. And that's sort of the area that my startup is in. And there's other patterns, like one more I want to add is the microservice chassis, which is the foundational framework that you build your microservices on. So on that note, that's my talk. So in summary, right, patterns and pattern languages are a great way to think about technology, discuss technology, and apply it. And the microservices pattern language is a good way to think about and discuss, and also whether to decide whether to use microservices, and if you do, how to go about using them. So that's my talk. Thank you for listening, and I hope that you found this useful. And here's my contact info.